Welcome. In the previous video, we looked at the governing equation uh, for groundwater flow, and we learned that we can describe the groundwater flow using like we try to solve for the head. That's the variable that we are trying to solve for, like the hydraulic head at any space, any point in space and time in our aquifer. Now, what I did in the previous video, I just showed you the governing equation, but I didn't show you how to solve it, like how to find the actual. I just showed you like a differential equation, yeah, that describes the rate of a change in head, giving like a boundary condition or initial condition or whatever. But I never showed you how to solve it, like how to find the actual head value. Like this is uh, let me go to the next slide. Like this is my aquifer here. Yeah. Let's say this is my aquifer here. How to find the actual head value here or here or here? What's the actual value, not just like the governing equation? Yeah. And that's what we'll show you in this video. So basically, like to find the actual head value, there are several ways for doing this. There's one way is called like analytical solution. Analytical solution is just what you learned in calculus courses. So what you learning in calculus courses, you will getting analytical solution, either like a closed form solution, like an equation that you can directly use, or an open or an infinite series solutions. That's what you did in calculus. So in calculus, for example, like you have a differential equation. How did you solve this in calculus courses? You integrate it, yeah? If you have a second order differential equation, what do? Like you integrate it time, you get your first derivative, then you integrate it twice, then you get your value, which is the h value that you're interested in. That's what you did in calculus. Yeah? You have a second order differential equation, you integrate it twice, yeah? So now, for real cases, we generally do like numerical solution, as I will show you, because for example, the governing equations that I showed you last video, it has no analytical solution, so we have to solve it numerically. Sometimes we also solve it graphically by just drawing it, yeah, drawing the solution. And I can easily show you this. I will show you this, and I will show you this also in the next video, like graphical solutions, yeah. So by the end of this video, you should be able to describe the difference between analytical solution, numerical solution, and like a graphical solution. And you should be able to solve it, like do an analytical solution for a simple case, yeah? Simple like 1D case. Okay. So let's look this what we did last time. So this is like the governing equation. In this governing equation, what we are trying to solve for, or what we are trying to determine is h. What is the head value here? Yeah. How head is it changing in space and time? And we see head like is varying in x, and this is the rate of a change and the rate of a change of x. But we see also hydraulic conductivity is also varying with x, because remember, like we talked, like this is our aquifer. It is not homogeneous. Like you can have like k value here, another k value here, a third k value here. That's like your x. Yeah. So it is not homogeneous. A K value not only it is not just homogeneous, it could be anisotropic, like the direction, like it would be flow dependent. So the hydraulic conductivity in the X would be different than in the Y direction than in the Z direction. So it is also directional dependent. Yeah, it depends on direction. Yeah. So we saw this equation, and this equation has no analytical solution. Like whatever you learned in this calculus course, like differential equation course, like you cannot apply them here because there's no analytical solution for it. And we need to solve this basically numerically. So we solve like that's exactly what MudFlow is doing. So MudFlow, which we will be using later, MudFlow is solving this equation numerically, and he's solving this equation, or like something that looks similar to this equation, yeah, because it has like some other source and sinks term and things like that. And he solves this equation for both cases of confined and unconfined aquifer, as I told you, and then it do some depth corrections. That's MudFlow 2005, yeah. Uh, Newer version might be doing something else, yeah. Uh, uh, So this is the governing equation, but it doesn't matter whether you want to solve this analytically, whether you want to solve this numerically, whether you want to solve this graphically. You need to define, of course, the aquifer properties. You need to define these K values, yeah? And you need to define like this is specific storage, yeah? So you need to define the aquifer property regardless, yeah? You need to define like an initial condition. So initial condition, they are important if you are doing a transient. If you are doing a steady state, they are uh, you will you will convert to like a steady state solution anywhere. So the initial condition will uh, not be like needed, yeah. And then you need to do like boundary condition. Okay, so that's like you describe like what is happening at your boundary. Let me show you like an example. Like, let's see, like this is a heat plate, yeah. So here we have a heat plate, yeah. And let's say this like boundary here, I have this is like insulated. Insulated means that there is a zero flux boundary, nothing enter and nothing exit of this boundary. Or not even a heat plate, yeah. Yeah, let's look at the heat plate and then heat plate, yeah. And let's say the initial condition of this heat plate is like zero. Yeah, the temperature here is zero. 0 degrees Celsius. Yes. And then I define like boundary condition. So I can say like my boundary condition here, I will apply like a constant heat source, and the temperature at this boundary would be like 10 degrees Celsius. And let's say the temperature at this boundary will be like 2 degrees Celsius. Yeah. So what will happen? Like when I apply this at the with time, like so this is 10. Yeah. So with time, this will start like not to be zero anymore. It will be start to be heated here, yeah. So the temperature will rise, and it will rise gradually until it reaches a steady state, yeah. So the temperature will keep rising in this direction. That's how heat will flow in this direction until like you build up the gradient, and then you reach like a steady state. Okay. And if you want to understand this better, watch like that would like please review the video that YouTube video about like differential equation, and that will help you to get this better. But generally speaking, heat will be transported in this direction, like from here to here, like from here to here. That's how like the heat will be transported. Yeah, heat transport. And then like you can draw like what would be the steady state. So now I'm doing the graphical solution. Like what would be the steady state here? So basically, like in order to do this, like you can do like you need to build like squares here. I'm just like this should need to be squares. So maybe that would be like 8. That would be like 8 degrees Celsius. That would be like 6, and that would be 4 degrees Celsius. And that makes sense, yeah, because my plate, like my temperature here at this boundary is 2. My temperature here at this boundary is 10. So this means that the highest temperature would be here and the lowest temperature would be here. And then you will see this temperature gradient developing. So the temperature here on this side would be more hot. The temperature here on this side would be more cold. That's the same for groundwater flow. Like imagine this is like, let's just remove this. Let's not make this temperature, make this head. Like this is head 10 meter here. This is head like 2 meter here. Oops. And that would be like 8 meter, 6 meter, and 4 meters. That would be like your head gradient, yeah? So that would be like your head gradient here. Okay, I don't know something here. That would be like your head gradient here. So that's like that's an graphical solution. What is a numerical solution? A numerical solution, uh, or what is an analytical solution? Analytical solution, that's exact solution. So like the analytical solution, it can give you, let's say this is again, this is like 10 meter. Analytical solution will you basically will give you the head at any point in space and at any point in time. So I will tell you like at this specific point in space and at 1.222 second, yeah, what is the head here, at this space and time. And then if you have an analytical solution, then you will find the exact solution. But again, this problem has no analytical solution, and we generally solve it numerically. Numerical solution is that it's like you don't get exact, you get an approximate solution over like discretized area. So to get a numerical solution, you need to discretize your model domain into like cells or elements. So if you are doing finite difference, that would be cells, for example. If you are doing finite elements, that would be different element, yeah? And then I will tell you what would be the temperature here, or the temperature here, or the temperature here. You just find the temperature in this cell, yeah? So the temperature in this cell could be like all of them might be similar, yeah? And I will say maybe like 9.5, yeah? How about here? Maybe like 9, yeah? Here maybe like whatever, yeah? So you just find it at like a discretize, like you discretize your domain. Not so that temperature 9.5, that would be for this whole cell. That would be for this whole cell. Yeah. So that's called an analytical solution. So let me wrap up. What did we learn here? What we learned here is that some of these differential equations, like to solve this differential equation, we need to integrate, like to solve them analytically or numerically, we need to do like an analytical integration using the laws of calculus, or we need to do a numerical integration, yeah? So in order to, instead of getting like this as a partial, you get like the h value, direct h value, because that's what we want to know, the head value, yeah? And in order to do this, we need to define, like if it's a transient case, we need the initial condition if we're interested in a transient solution. If it's a steady state, it doesn't matter because it will convert to the steady state anyway. And then we need to define like the boundary condition as well. Yeah, so we need to define our boundary condition to solve this equation. Yeah. If this is still like unclear, what you can do, you can ask a question or ask the instructor or ask generative AI. Like you can ask AI, chat with AI and tell him, explain to me the difference between numerical and analytical solution for groundwater flow equation. Yeah. And then you might get some answers. Yeah. Okay. Or check your textbook, read more in your textbook, yeah, in any of your two textbook. Okay, so let's look here. This is the initial condition. So initial condition, so here at time zero, for example, that was my head here. So you go to the field or you do your experiment or whatever, and then at time zero, that was the head level, and then at time t, the head, I started to do some pumping, and then at time t, the head dropped. So that's like my initial condition. So for any transient problem, initial head distribution must be known to solve for head change with time. For steady state, it doesn't matter because it will convert anyway. Like steady state, like let's say here, that's the steady state. Like this is 10 and this is 2. Do we need to know the initial condition? No, we don't need, because like it will convert anyway. My solution, I know it will look something like this. Yeah, that would be like 10, that would be 8, that would be like, I don't know, maybe that would be 6 and that would be 4. Yeah, so that it really does not matter. Yeah. Uh, so it does not matter. Yeah. Okay, because it's that's a steady state. It's not a changing with time. Like head here would be 8 at any time, invariant of time, because that's a steady state. Head here would be 6. But if that is a changing in time, like this 10 became like 11, then this 8 will no longer become 11. It might become like 9.5 or whatever. Yeah, that's like a transient solution. Okay. Uh, Now, boundary conditions, there are like three types of boundary condition. There is like specified head. So specified head, I basically specify the head here at this boundary. So I say like, okay, like this boundary, the head here is this boundary is 10 meter. Yeah. So this is the head at this boundary, for example. And for example, like at this boundary here, like the head here is like this, like let's call this north, south, east, west, like this head in the west boundary, head in the north, in the south boundary, let's say equal to 5, yeah? And like, let's say this boundary, like here's another boundary, and I say like head here is equal to, I don't know, 8. And when we get to the modeling part, I will show you like how to identify or know your boundary condition. Yeah, so we will like look at this when we get to the modeling part. Like here, I'm just putting any value just to illustrate the concept. Yeah. So that's like one type of boundary condition. Another type, like this called like type 1 boundary condition. Second boundary condition or type 2 boundary condition, I specify the flux. So instead of specifying the head, I will specify the flux. So let's say across this boundary, for example, we here, like across this boundary, yeah, sorry. So across this boundary, which is also like this, like here, this boundary, yeah. So across this boundary, I'm getting like 100 million gallon per day. Yeah, that's like how much water I'm getting like across this boundary. And then so I specify this boundary, and then what? The head will be like determined accordingly. So you just specify the boundary, and then the head will be calculated or determined according. In type 1 boundary condition, you specify the head, and based on this head that you specify, the flux, what's coming in, would be calculated accordingly. So basically, like for type 1 boundary, you say, okay, I have this head here, and then when you solve the problem, it will tell you how much flux will be entering or leaving or whatever this boundary. Yeah. So that versus like in type 2 boundary, you specify the flux. You said, okay, I have like 100 million gallon per day entering through like this boundary here. Yeah. Entering through this boundary. Then your like the head will be calculated accordingly, according to so the head that would maintain this flux would be calculated according. So boundary, there's boundary condition type 3, like type 3 boundary is specified head dependent flux. So the head will depend on the flux, the amount of water that's flowing will be head dependent. What does this mean? You usually find this like at a stream, for example. So let's say like you have a stream here, and this is oops, that's like you have like stream here, that's like your land surface, that is like your stream level here, that's your water table. So let's say this is your water, so you have like head in the aquifer, and you have head in the river. So based on like the difference, and here you have river conductance, so water could flow from here to here or from here to here depending on the head in the aquifer, the head in the river, and this bed conductance. So this is called like a specified head dependent flux. So depending on the head in the aquifer minus like the head in the river and the conductance of this river bed, then the flux will be determined. This is called like a type 3 boundary condition. So it's a mixture of type 1 and type 2. So type 1, you specify the head and the flux will be determined. Type 2, you specify the flux and the head will be determined. Type 3, the flux will depend on the relative value of like your changes in head. Yeah. Between like the river, for example, and the aquifer. Okay. So that is three types of boundary condition. Yeah. Uh, uh, that's like three types of boundary condition. Okay, so let's look here. Yeah. So when do we use analytical solution and when do we use numerical solution? So in my career, I use both. I use like both are helpful and each one has its use. Yeah. And the course I used like I used to be like use the course part of the course that I used to teach at Florida State University is called like a this was a graduate course called like groundwater modeling, and I used to teach analytical solutions. Yeah, analytical solution for very like advanced case, like advanced analytical solution. It was mostly like a math class where I teach for advanced case. But so numerical. But in my career, in my like research career, I and practical career, I use both. Yeah, I use like. Uh, Analytical solution and numerical solution. In analytical solution, you have like they will give you exact solution for simplified cases. They are very quick because it's just they don't need any computational time. Yeah. You just like instantaneous. You get the answer instantaneously. Numerical solutions. This is for real life application. Yeah. Uh, Numerical solutions, this could be like finite element, finite difference. Again, this like numerical solution, like this is beyond the scope of this course to cover a numerical solution. But I will not show you like how to do numerical solution. We show like for graduate student, we show this as another course called Advanced Engineering Analysis. I touch on numerical solution and give you a flavor of it. And then these videos, for if you are curious like to learn this, these videos are available on my YouTube channel for this course, Advanced Engineering Analysis. But it's not important. Yeah, like for this course, basically what MudFlow will do, it will solve this equation for us numerically using a numerical solution. For this course, for real life application for your modeling case study, what you will do, like MudFlow will solve this equation for you numerically. If you want to know how MudFlow solves this numerically, you can check like the manual of MudFlow, but you don't need this. Like at this level, like since this is your first groundwater course, you generally don't need to know these details. You just need to know that MudFlow is solving this equation for you numerically. Yeah. Uh, but I will show you like what I will show you in this lesson. I will show you like analytical solutions. That's what I will be showing you in this lesson. I will be showing you analytical solution for a simple case. So basically, like we will for confined and unconfined aquifer for 1D flow, we will see like how the analytical solution for this groundwater flow equation will look like. Yeah, to find the head. Yeah. Okay. Again, as I told you, this is the difference between analytical and numerical solution. For both of them, you need to define like boundary condition and initial condition if you're doing transient solution. Analytical solution, you find the exact value. Like so, you find the exact value at the exact value at the exact space and time. Yeah. For numerical solution, you have to discretize your aquifer. So you have to discretize your domain into cells like this. So you see here, this is the cell. And you see here, it does see you have like this boundary here, which is something extra. But what it doesn't matter because what you are finding, you are just finding the head here at this point. You are finding the head at this point for all these cell or these element if you're using a finite element method. Yeah. So you're finding the head. Like see here, maybe this is the area where we are most interested in, and see here your cells is becoming smaller to find to be like more get like higher spatial resolution similarly with time. So this is discretized space, but here you will also discretize it in time, like time steps. Yeah, so that time steps could be like maybe 1 day, or it could be like 1 month, or it could be 6 months, or it could be 10 minutes, depending on the objective of your study and depending on what you will do, you will discretize your time. And that will give you the head value at this time period, that like 1 day, for this whole day. Yeah. If you wanted each 12 hours, then you discretize it each 12 hour, and that will give you the head value for these 12 hours. While analytical solution, it gives you the exact value. Like I tell you, what is the head, you know, like that's something like this. What is the head at x equal like 1.335, y equal like 0.005, for example, and time equal 1.88 like minute. Yeah. So analytical solution, it can give you this. Numerical solution, it just has to be like discretization. So maybe this would be like this cell, so that would, and then your time discretization would might not be like, it will give you for the whole day, or depending like how you discretize it. This like if you're discretizing this minute by minute, then it will not give you at 1.88 minute, it will just give you this at minute 2. Yeah, for the numerical solution. It's like an approximate solution. Yeah. Okay, so now let's get to business. Yeah. Let's just look at let's get to business. Yeah. So let's just look here at let's get to business, and let's look at finding the analytical solution for this guy. Can we find the analytical solution for this guy? Yeah. Yes or no? No, we cannot because it has no analytical solution. Yeah. But we can simplify it. Yeah. So we can simplify this guy, and then so we can assume that it is this is like a steady state. Yeah. It's not transient. Yeah. So it's not head is not changing with time. It's constant. We can assume it's just 1D. Yeah. It's just 1D flow. Yeah. There's only flow in the x direction. There's no vertical flow, or there's no flow in the y direction. Yeah. Okay. So we got something like this, yeah. So can we solve this analytically? No, we cannot. It has no analytical solution also. Why? Because k here is changing with x. There's no analytical solution for this. So for this one to have an analytical solution, we need to assume that partial k over partial x is equal to 0. Like k is not changing with x. What does this mean? It means it's homogeneous. So we need to do this for 1D steady state homogeneous. Yeah. So for 1D steady state homogeneous, we can solve this one. Yeah. And again, remember I told you for a numerical solution, a graphical solution, analytical solution, what do we need for steady state? For transient state, we would need initial condition, but for steady state, what do we need? For steady state, we need boundary condition, yeah. And for transient state, in addition to boundary condition, we will also need, uh, in addition to boundary condition, we will also need what? Initial condition, yeah. Initial condition, yeah. Okay, so that's my boundary conditions that I defined here. So let's say this is my aquifer here. So, and this is my x, like x equal to 0. So at x equal to 0, I have like h1. And then at x equal to L, I have like h2. Yeah. So here is my initial, my boundary condition. So at this boundary at x equal to 0, I have h1, and x equal to L, I have h2. Yeah, that's L. Yeah, so that's like the distance from here to here. Okay. So that would be like the governing equation. I'm just keeping this k here, like k could go 0, but I would like to keep it here because I will show you at the end how it will go anyway. I'd like to keep it here. It's a constant, yeah. So that's the general solution, like how to solve this. So do you remember how to solve this from your calculus courses? So from your calculus course to solve this, like you need to integrate this once, and then you integrate it twice, and then you will, like when you integrate it once, like let me show you here. So like you integrate this guy once, and then if you integrated this guy once, what do you get? Like you get your first derivative, yeah. So if I integrated like this guy here, I get this guy here. And then if I integrated this guy here, you integrated 0, you get a constant, like you get this guy here. Then this guy, what do? I integrate like this guy again. And if I integrated this guy again, I will get the h, yeah? And if I integrated this guy again with respect to x, yeah? Like see here. So if I integrated this guy, I get an h. And if I integrated this guy with respect to x, then I get uh, I get uh, I get like c1 times x, because this is like, remember, like here is this x to the power 0, you integrate it, then it become x, yeah. And then 0, when you integrate it, it become a constant, and then plus constant, yeah, because this is a constant. And then I multiplied by k, so this is c1 x over k, and then constant here divided by k, I still get a constant, yeah, like c2 divided by k, like a constant divided by k, that will also give me a constant, yeah, because k is constant, you divide by constant, you get another constant. So I get an equation that looks like this. Does this look good? No, it does not. Why? I have a problem. I have one equation, I have three unknown, like, so k is value, like k, this is a parameter, this is known, yeah, you know this. X is known, like you can put any x value in your domain, yeah. But this is unknown, this is unknown, this is unknown. So how can I solve this problem? Do I have any extra information? I do. I have a boundary condition. So here is my boundary condition. So here, this is as x equal to 0, I have like h1, and here x equal to L, I have like h2. So I have two boundary conditions. So now let's do this. Like, so for the boundary condition at h x equal to 0, I have h1, at x equal to L, I have H2. So let's just substitute with my boundary condition. So let's uh, remember you did this in calculus before. You just like substitute here like H is equal to like C1 over K, X is equal to 0 plus C2. So this give me like C2 is equal to H, yeah? Uh, sorry, in this case it's H1, yeah? Then C2 is equal to H1, yeah? And then, so now I know like C2 is equal to H1, and I can just like substitute, like this is C2 is equal to H1, so I can just substitute this. So now I have an equation that looks like this. Looks much better, yeah? I have H1 is known, like this is known, like so this value is giving, my boundary condition is known. So I know this guy, I know this guy, this is X, and I know this guy. I still have another problem. I have like one equation and two unknown, but I have another boundary condition like this one. So now I use my other boundary condition, yeah? So if I use my other boundary condition, let me, where is this? Yeah, so this is like using my other boundary condition. So at H2, yeah, so I substitute to like H2. So H here, like I will get like H2. That would be like H2. That would be C1. That's the ones that I'm trying to solve for over K times L plus what is C2? We got C2 like already H1. So we got something that looks like this here. And then I can solve for C. So I have like C is equal to something like this. And then C1, I can just back substitute this guy here. So if I back substitute this Y here, then I got something like this. And so it turned out that this is something very trivial. This is just an equation of a straight line. Yeah, this is just like an equation of a straight line, which is exactly what we see here. This is just a straight line. So the solution of this guy, the analytical solution of this guy, so this is called an analytical solution. Why is that analytical solution? Again, let me repeat this because this might still not be clear for you. Like analytical solutions, this is a closed form solution because at any point of x, I can just find h because I know h1 here, yeah, and I know h2 here, like these values are giving, and then I tell you at this x, what is h here. So basically, you substitute h1, you substitute h2, you know L is given, you know L, and then you just substitute the x value. Like let's say this x value is like 1.33335, yeah? You just substitute here like 1.335, and then it will give you the exact value of h here, yeah? That piece will give you the exact value of h. That's called an analytical solution, but it turned out that this is just something very trivial, yeah? Turned out that this is just an equation of a straight line. This is like here, this is your slope and this is your intercept. That's it. That's so all what we are doing here turned out that the solution at the end for this guy in the steady state is just a straight line. Remember, I had my k here, yeah? Where is my k? It disappeared. You don't need it. See, I told you I will put the k here just to show you at the end that you don't need it. But you could have known this already from the beginning, yeah? Instead of going through all this, you can just know that this is like goes with here. But it's just like for a steady state, really, basically, if I know the head here and I know the head here, I just have a straight line which I can interpolate. Like I just need to find like the slope of this straight line and the intercept, and then I can interpolate. And that's exactly how I solved this. Hey, this is a 1D case. This is a 2D case. Yeah, like this heat plate. I know my head here is like 10 like degrees Celsius. I know my head here is like I don't know, like 2 degrees Celsius. I know that everything in between would be just like interpolation. I'll be just interpolating. So that would be like 8, that would be 6, and that would be 4. And that's how I was able to draw this easily. Yeah, just by my intuition, using my intuition. Because it's just a straight line. And that's how head is changing in space. Again, here head is not a changing a time because that's a steady state. If we are looking for a transient state, that would be different. and the analytical solution for this would also look very different than this one. Yeah. You can go to my research website and you can find like some, I think I have about 5 or 6 lessons about analytical tool. Not for the groundwater flow equation, for the transport equation. Yeah, for the transport, not for this one, but for the transport equation. But there are books, yeah, like so there are books that you can find online. That I have one of them in my office. If you are interested, please stop by my office and I can show you like a book about analytical solution for this groundwater flow equations. Yeah. Uh, I use this book, for example, to prepare lessons for advanced engineering analysis. I have it in my office. If you want to stop by and have a look at it, please do so. Yeah. Analytical solution. But anyway, doesn't matter. I just want to show you what analytical solution is. So it is linear with x and no k in the equation. Yeah. Okay. Now, uh, so here we just like I'm just like showing this again. So for this one, that's like your boundary condition. You get something that looks like this, and then if you like rearrange it, these terms here, then you can get it into something that looks familiar to you. Because remember, do you remember like this guy? Like so, I can just rearrange it. Like this is like delta H here, or negative delta H, actually or just like delta H over L. And you know, what is delta H over L? Like, does this look familiar? Like K is equal to negative K delta H over L. Yeah. So I can just like express like this guy, and this is like, this is negative. Yeah. So this is negative. So like, let me let me just put like this is in this way. Let me just write it in this way. H2 minus H1, and this would be negative. Yeah. So negative, like this guy here, that will give you this guy. So now I can write it in this form, and then I can rearrange my term. So now I have like, now this is, again, this is the similar solution to this one, but here it's not a function of k. Like here, I know like my boundary condition 1 and my boundary condition 2, and then I can solve for h. Here in this form, I know my q, yeah, and I know like my boundary condition 1, then I can solve for h. So here, if two boundary conditions are defined, like h1 and h2, you can solve for h. Here in this form of my equation, I have q is defined and I have boundary condition 1 is defined, then I can solve for h. Yeah. And then you also remember this big Q is like small q time area, and the area, that's like aquifer thickness times the width. So that's like how deep. So that's like your aquifer here. So that would be the B and that would be the W. Yeah. And then you can also express it in this way. So you basically has two form, like two analytical solutions. They are not two analytical solutions. We just like change it as form, like, because we know Darcy law, so we know we can change like this guy by like this guy. So we end up like, you can have like this guy, like the analytical solution for this guy could be like either this one or this one. Yeah. This one is based like, you need like two boundary condition is defined, and this one like just one boundary condition, and your flux density like is defined. Yeah. So, and again, you can reach to the same conclusion. This is just what I was showing you here from Darcy law. Yeah. So that's like Darcy law, and you can reach the same conclusion. So it turned out that basically like the solution for this guy, yeah, the 1D solution for this guy is just like a form of a Darcy law. Yeah, this form of a Darcy law. Like, so if I solve with this guy just as I showed you, if I solve with this guy as I showed you, you get this solution. This solution is just like a different form of Darcy law. That's it. Yeah, so you have like these two solutions. Like, again, so I have this guy here. This k should be out. Shouldn't be here inside. I have this guy here, and like if this guy with this boundary condition, I integrate it twice, I will get this form just as I showed you. And like this form is basically equivalent to, it's another way of writing Darcy law. Yeah, that's another way of writing Darcy law. Uh, and also one thing I can also to show you, like this is remember this is Q is A, like the aquifer thickness times W. Sometimes like we just flow per unit width. So you have like Q, big Q, you have a small q, and you have Q prime, and Q prime, that's like you just assume. So this is like here. This is your B, and this is like your W. Yeah. So if W is equal to 1, just like unit width inside, that's your B here. So this is like Q prime, and this is like a flow per unit width. This is like flow rate Q. This is flow per unit width, and that's like your specific discharge, yeah, flux density, specific discharge. Okay. Uh, so in summary, yeah, analytical solution for steady state flow in homogeneous and not anisotropic. This is a typo. And isotropic confined aquifer for a specified head boundary condition. You have like this is the governing equation. This is like your boundary condition. Hydraulic head at any x, we can basically solve this, and then we can find an equation, a closed form. This is called a closed form solution for hydraulic head at any x. Yeah, and this is per unit width, just like so. You can have it in this form, or you can have it in this form. So if you know like Q or big Q, small q, whichever Q, doesn't matter, and like one boundary, then you can find H, or if you know two boundary, you can find H. And you can also solve for Q. You can just like, yeah, if you know like that's Darcy law. We are just getting to Darcy law. Okay, so I hope you able to see that this turned like the solution for this case turned to be something very trivial, which is Darcy law. Yeah. But this just for this case, like where it's homogeneous, where it is isotropic, and where it is steady state. Yeah, but for other cases it will not. So this is just an exercise. You can solve it. A confined aquifer. So try to solve it. Is this Darcy law? We did this before, so there's really nothing new here. I don't want to like spend time to do this. You should by now you should be able to do these things on your own. So just try to solve it. Like pause the video, try to solve it, and that would be also good practice for you for your homework and for your exam. Yeah. So try to solve it. Okay. So if you solve it, the solution should look something like this. And it's also asking you what is the elevation of the potentiometric surface at a point like so. This is another question. So also try to solve it like look back for that's the equations that you need to use. So try to solve it on your own. And if you solve it in your own, like the right solution should look like this. Yeah. Okay. And again, now try to solve this one, like try to solve this one like using this equation. Remember, like there's two equations, like this one or this one. So try to solve this one using this equation, and you should get the same number. Okay, now let's do like now this gets a little bit tricky uh, because remember, like unconfined aquifer is generally more tricky. So in unconfined aquifer, you do like depth integrated coefficient. So here, this is like the general equations that we saw before. I just added like source and sink term to it. And we've seen this before. This is with the Dipwee assumption. This is a governing equation for unconfined aquifer, and you see like here H is changing with X, and you have like specific yield here. Here you have specific storage. And again, here you have also some source and sink term. Yeah. Now, for this one, I want to like, so here, that's your governing equation would look something like this. And let's see here, there is like recharge. So that's like, that would be an example. Like, let's say you went to like small island, like one of these small Caribbean island or American Samoa, or I don't know, any of this island, and then they tell you we want to know the head levels uh, here, giving like a certain recharge rate, because like with certain recharge rate like we got flooding, or with when recharge rate is very low like we get very dry and we cannot tap into like our freshwater resources. So can you calculate like the head here, like our groundwater level or water table at different like recharge conditions? That would be so, like an island looks something like this. So here down below it would look something like this. Can you do this? Yes, because you have a governing equation. So here what we did like for this one, this unconfined aquifer, we just solving it for like 1D flow, and we assume that it is like under steady state condition, and here we are testing different like recharge condition, like different W. So here W becomes an area related to specific injection or extraction rate. So that could be pumping, that could be like recharge, like rainfalls that's recharging the aquifer. So you get like an equation that looks something like this. So if you check your textbook, you will see like how to integrate, like how to solve this. You just integrate it twice. Yeah. So in your textbook, it shows like I'm skipping these details here. Check advanced engineering analysis. I think I showed you how to solve this analytically. But again, it's not important. You don't need to do this. I mean, it's not really, this is not a math class, and this is not what we are looking at here. So, but now what I want you to be clear about is that like to solve this, you need to integrate it twice, yeah, as I did previously. And check your textbook. It shows you this in step by step if you want, if you're curious about the math. But I'm skipping the math part here, just for the interest of time and because it's not important for what we are doing here. Here we try to develop a conceptual understanding more than like this math things. So I don't want to distract you with these math things. But anyway, so that's the analytical solution for this. Like if you integrated this twice, you will get this H. So here H is a function of what? It's a function of H1, H2, the length between like H1 and H2. Hydraulic conductivity now here is a factor, and like recharge. That's like the recharge, like, or this like source and sink term. Now you see here when you have recharge, so let's say there is rainfall and then water started to infiltrate here. What do you get here? You get a groundwater divide. So you get this mound here. So you get like a mound here, and this serve as a groundwater divide. So there is a no flow boundary. So basically what will happen here, this drop of rain that just fall here, it will flow to this direction, and the drop of rain that just flow to the other side of this no flow boundary, it will flow to this direction. So basically that's how your aquifer will get like recharged. And in the next video, I will show you like an animation for this. Like I will show you this problem, and I will show you like an animation for this problem. Yeah. But this is not important. Like the important part, because I will show you this next video. The important part is that we have an equation, we have an analytical form, a closed form solution that we can use to determine the head at any part of my aquifer. So if I told you what is the head here, you will be able to know it. What is the head here? You'll be able to know it. What is the head here? You'll be able to know. What's the head here? You'll be able to know it. What's the head here? You'll be able to know. You just, all you need is like to know how much water is the recharge amount, the W, and like this boundary here. So all you need, like you know this one, you know this one, you know this one, then the head here could be calculated. Your water level inside this unconfined aquifer could be calculated. Not only this, I could also calculate like flow rate per unit width. So like flow rate, like if I told you like, okay, how much water will be exiting through this phase? And that's important because this water will be exiting here. This is called like submarine groundwater discharge, and it's important for marine ecosystem. So if I told you how much water will be exiting through here or how much water will be flowing here, then there's an equation, flow rate per unit width. And in your homework, I will you will be using this equation to just crunching some numbers. Yeah, so because if you start like just listening to me will not help you much. If you start to play with this equation, you get a better feeling for them. But anyway, uh, uh, distance from the origin to the water divide. Like if I want to know this distance, like where is this water divide located? Is it here? Is it here? Is it here? Is it here? Well, I can also find like another equation for this one, and that's like the distance to the groundwater divide, and uh, okay. And then what is the maximum elevation of the water table at the groundwater divide? If I want to, that's the maximum table, that's the maximum elevation. So like this is the place where maybe like flooding might occur, because that's where you have like the maximum. Like if this water table is high, let's say like it started to overflow, so that's where you'll get like your maximum flooding would be somewhere here. Yeah. The water table started to occur. So maximum elevation of water table divide. Yeah. Um, okay, so that is basically that is this one. Yeah. So let's here like so solving for H and Q at steady state flow and unconfined aquifer with no recharge. If there's no recharge, now here see the H here. You have like H square. So if there's no recharge, so basically no recharge, it is the same equation. Like you just get rid of like this W would be zero. Yeah. And like here this would be like 0, and this will not be meaningful, and this will not be meaningful, so because this will not be meaningful. But here, if there's no recharge, like basically like you get rid of like these two terms, then now you see here, like remember the previous one, I told you that like the solution for the unconfined aquifer was just a straight line. So you have like equation for a straight line. Here is not a straight line. Here you have a parabola. You have this like shape like here, and here like you have like it's you don't have like a linear relationship anymore. You have like this non-linear relationship. Okay, and that's what you see here. Like you don't see like straight line. You don't see like the slope is not constant. That's what I was telling you before. The slope here is constant. The slope here is not constant. Here is mild. Here is like steep. Like see the slope here is like steep. The slope here is the steepest, and here is very steep. It's the steepest, so mild, milder. So, and that's why you got like this like non-linearity. So if you compare this one here, like let me show you. So you see here, this is linear, while see here, this is linear, H. Yeah, so this is linear, while like this is for the confined aquifer, while here this is like non-linear, and that's why you see this non-linearity in your water table. And same, you can calculate like a flow per unit width. Okay, so let's look at an example. Like this is similar to your homework. So here I'm giving you like the length, I'm giving you H1, H2, I'm giving you K, and I'm giving you different recharge value per day. Like so recharge is 0, recharge is some value in between, and then recharge is large. So large, medium, and 0. Yeah, large, big recharge, small like recharge, and like 0 recharge. And I'm asking you to calculate like the groundwater head, like the head, like to draw the groundwater table. So how can you do this? You can just simply say, okay, at 0 I know the head is 10, so this is given already. At H2, I know the head is 0. And then anywhere in between, so I did this with Excel. So you can just like say here, like at X is equal to 200, 400, 600. Like, so you can plug these numbers into Excel. So you plug like X is equal to 200, L is giving, W is giving, K is giving, these are giving, these are giving, X here you plug 200, and then, so let's say I'm doing for this guy. Then I will calculate like this value here. And then I do the same, I will calculate this value here, I will do the same, I will calculate this value here, I will do the same, I will calculate this value here, and Excel will just plot this line for me. That's how I did it. Yeah. Calculate this value. So now for the, now, and I did the same for this W, and I did the same for 0. So now I'm asking you question like where is the groundwater divide? So you see here for this one, like the groundwater divide, that's where like you have your maximum amount. So for this guy, it should be somewhere here. Yeah. And we have an equation for it. Like we can, that would be my D. Yeah. So that's my D for W equal to 0.03. Yeah. What about this guy? So for this guy, it's here. That's my D here. So for this guy is here. So that is D for W equal to 0.015. What about this guy? Like when there's no charge. Here there's no groundwater amount. Why? Because water will just recharge and it will flow from here to here. All the water will be just like flowing from here to here as I showed you in the previous slide here. Yeah. So here when, or maybe I didn't show it to you. So here when there is no recharge, like W here is equal to 0, then just water will flow like this. That's basically would be how, that's how like the groundwater will flow. Versus the other one, like when if there is recharge, then you will have this groundwater divide. So that's what we see here. Here just water, for this case, will just be flowing like this. Yeah. So so here for this guy, I just showed you here, if you have high recharge, your this will be somewhere here. Like this mound will be like somewhere here. Uh, for this guy is somewhere here. So like here, this is this one. For the high recharge, this would be like this one here, and for this one, this would be this one here. And then be very close. Sorry, for this one is this one here. Yeah. And then like what would be the head? Like what would be the head here? The head here for this one, it would be like 10. Yeah. And the head here for this one would be like 11. Okay. So that is this problem. So here I'm just showing you, this is for the head. Here I'm just showing you the same story, but for the discharge, because we have an equation here. Uh, and for this equation, you can just like, it's just crunching some numbers. So you are expert in this. Like, I wouldn't waste your time like crunching some numbers here. But I just want to show you that here, that the discharge will be also different because you have high recharge, then it's, you would expect, yeah, to get. So like you see, for example, like if you compare this one and this one is you get like a higher discharge, yeah. You get a higher discharge. Why? Because your discharge will be higher. Let's look here, for example. I see here, that's a clear one. Your discharge will be higher because you have more recharge. Yeah, so it makes sense. Like for at the same location, you'll have like a high discharge. Why discharge here is negative? Like why do we get negative discharge? Discharge is negative because we define our positive x direction here. So let me show you. So like you have the water, so that's our positive x direction. So x direction is divided as positive here. So you have like q here and q here. Q here would be like positive, and Q here would be negative. Negative just means that it is going in this direction, like the flow is in this direction. Positive means that just the flow is in this direction where we defined our x. That's why that's the difference between like negative and positive. Okay, so you can just like pause this video. I don't want to keep this video long. Like you can pause this video. I think this is the last slide that I have here. Yeah, so just pause it and look at it. And then to practice, I give you like some homework problem which can help you to practice. And then uh, you can practice also giving these numbers. So you can plug these numbers in this equation and make sure that you're getting these same numbers before you do your homework. Uh, so you can practice here, you can practice with your homework, and I think you have something like this in your exam also. So you get it, like that's how you prepare for your exam. It's a take-home exam anyway, so it doesn't matter. Or it's take-home exam or in-person exam, like that would be dependent on how we arrange it, yeah? So we will like arrange it for some That's how we it will be arranged. Yeah. So check your Canvas to know whether your exam will be like take home or whether it will be in class. Yeah. Okay. Uh, so I think that's it for this video. I hope I'm not keeping it long. Yes. So I will just stop